It's a pretty intimidating concept because people have traditionally found it to be difficult. It's partly quality of instruction, partly because it can be a little crazy. And in a lot of cases, I find that the kind of person who tends to want to do all the math first, then start writing stuff down, meaning like they want to figure it all out in their head and then just write down an answer. The probability doesn't really work very well for those individuals, except for the handful of people who are just like gifted in that way, like living computers. So there's exceptions to everything, but generally there needs to be some sort of organized approach whenever you're tackling a probability question, because it is, after all, logic based, right? If you think of probability as logic with numbers, then that's a good way of kind of approaching things. I put this little cartoon in there because one, I felt like I needed to have a cartoon, something to kind of introduce the topic, but also the little quote, I wish we hadn't learned probability because I don't think our odds are good. The kid was using, principal's office, the kid was using the concept of odds and probability correctly. It's just, I like this particular cartoon because, well, obviously the principal part, kids get in trouble, is kind of funny. But also you have the idea that people often confuse concepts of probability with odds, and so they don't mean the same thing, but one is in support of the other, right? So we use probabilities to help us determine odds, but probability and odds are not synonyms for one another, right? And that's one of the things that we're going to tackle as we go forward. Applications of probability. This is one of the few topics where I don't think I need to get too creative to come up with real life useful applications of probability. Like there's some other topics and some other classes where I'm like, all right, let me see if they'll buy this line of crap. Here, it's more like, you just walk into a casino, you got your probability right there. Maybe you don't want to do the casino thing. Maybe you just play simple lotteries. Okay, well, you got it right there. Maybe you don't like to gamble at all. I don't like to gamble. Figure I work too hard to earn the money to begin with. Why am I going to piss it away? So maybe you just think in terms of weather. 70% chance of precipitation. Right? Where do they get that number from? I'd be really interested to know. Right? The weatherman is always wrong. Well, I guess that was true back in the 80s and 90s. But nowadays, they're not really that wrong very frequently. The only way that they're ever really quote unquote wrong is when they sensationalize things. And they're like, this is going to be the worst hurricane in the history of mankind. And then you get like high winds and a thunder shower. And you're like, well, if you just said high winds and a thunder shower, then you would have been fine. But what they do is they look at the worst case scenario because that's the clickbait, So there are exceptions to everything, but there's a great deal of probability that goes along in that. And when I talk about probability in that context, I'm talking about using past outcomes to help determine future events, right? In order to understand any of the stuff that I just talked about, we need to get into the vocabulary and the nomenclature and all that stuff, right? So it's right back to basics, right? So we're talking like 7th grade math, which is great, because that means it's going to start off pretty easy. We just got to make sure that when it goes from easy to not easy, we don't miss that transition, right? Because in probability, it's like, all right, I'm with you. Oh, wait, well, hold on. What just happened? So the zoning out is not a good strategy when it comes to probability, because it goes from really easy to the opposite of that, just like that, all right? So probability branch of math that deals with the chance of an event occurring. An event is a collection of outcomes of a procedure. So this is just vocabulary stuff. Sample space, complete list of all possible outcomes in an experiment or activity. All right. So that's telling me that if I'm talking about weather, for example, that if I'm considering a sample space, I'm considering all possible events that could occur related to weather. All right. So if you think about it, it's like, all right, so we got light rain, moderate rain, heavy rain, thunder shower, hail, snow, sleet, wintry mix, no snow, no precipitation whatsoever, heat wave, right? A world record type heat wave, or just like a hot day, you know. Uh, you also have humidity, but that doesn't necessarily lead to precipitation. So it's a hot, hazy, and humid. You know, that old chestnut there. Then you have you know, the dry days, the allergy days, you know, like what's going on? What's the quality of the air? You know, is it a heat advisory? Is it stay indoors? You know, like all that kind of stuff. Every possible outcome would make up your sample space. So when it comes to things like weather, it's pretty challenging. But when it comes to, like, let's say rolling a die or flipping a coin, I flip a coin, my sample space is just heads or tails. Those are my two outcomes. Roll a die, my possible sample space would be the numbers 1, 2, 3, 4, 5, or 6. That's it. There's nothing beyond. It's very discrete, right? For the notation, P, I think it makes all the sense in the world to let P represent probability, right? Later on in the course, Unit 3, we're going to let P represent something else, proportion, but it's basically going to amount to the same thing. A, B, C, D, E, F, whatever. Those are what we use to denote specific events, but oftentimes what we do is we just, you know, just like a let statement for solving a word problem, we just choose a letter that's emblematic of the variable in the problem, right? So if you're flipping a coin and you want to know getting heads or tails, P of H for heads, probability of heads, P of T, probability of tails. So that brings me to the next one. P parentheses A is the probability of event A occurring, right? The P parentheses is not multiplication, it's function notation. You know, so if you think back to algebra, it's like f of x, all right? So P of A, not P times A. We also have that little tilde that represents not, right? So it's a complement, it's the opposite of something happening. So if I say that the probability it's going to rain is, and I give a number, then I could also ask you, what's the probability that it's not going to rain? All right. So if I let R represent raining, then not R would be not raining, right? But then if you have binary situations, like, for example, heads or tails, where there's only two possible outcomes, I could, for example, if I wanted to say not heads, I could do that one of two ways. I could use a little tilde in front of the H to denote the not, or I can just say T, because I know, well, if it's not heads, it's going to be tails. You know, so that's another possible way that you can look at it. In terms of finding probabilities, so I break it down into, you know, these three simple categories, but each one of these categories is like a course of study in and of themselves. So right here, I'm just giving you a little taste of what each one is all about, right? Experimentation, we have formulaic approach, and we have estimation pattern recognition. So the experimentation is, I have no idea what the probability is. Let me try the experiment a couple times and see what happens. You know, so the example here is flip a coin 200 times, get an idea what the probability of getting heads is. So if I flip a coin, I know that there's one head and there's two sides, and so it's a 1 out of 2. But maybe it's something more complicated than that. Or maybe I just didn't know. All right. Or maybe I want to test to see if this is really a fair coin. Maybe it's like one of those weighted coins. It's a little heavier on one side, so a trick coin. So I'm like, you know what? I think it's 1 out of 2, but I'm not really 100% sure. Let me flip it a bunch of times and see what happens. All right. So I flip it 10 times, and 8 out of 10 times I get heads. So I'm like, all right, I might be onto something here, but that's not enough trials, because it's possible that I could flip a regular coin 10 times and get 8 heads. You know, it doesn't have to break down to a 50-50. You know, nature comes into play here, right? You know, it could also be maybe it's not even a trick coin. Maybe I'm just a tricky person that came up with a technique that allows me to get the heads a little bit more frequently than the tails. And I want to test to see if there's really merit to my claim. You know, so I flip it 50 times, and 40 of the times that I flipped it, I got heads. So I'm feeling pretty good about my 80% mark, but I'm still not 100% convinced. So I'll flip it another 50 times. I'll flip it another 900 times, get up to 1,000. You know, then you know what I'll do? I'll even mix it up. I'll take that coin and I'll give it to somebody else and have them flip it just to make sure that maybe I'm not doing something that's causing, you know, like I think it's a real legit trick coin. I'll have somebody else flip it and make sure that I'm not influencing the outcomes in some way. Right? A lot of different ways you can handle it, but the bottom line is we want to try not a few times, we want to try lots and lots of times, hundreds of times, thousands of times, right? And so what we end up doing, instead of actually flipping coins, is we build what we call simulators, right? We use technology to do the simulations for us, because flipping a coin 1,000 times, I'd say flipping a coin 100 times. I don't want to do that. It takes forever, right? Doing it 1,000 times, 10,000 times, 100,000 times. It's going to take a lifetime. I don't want to get into that. So what I do is I develop a simulation where a computer or artificial intelligence or even just a simple program in a calculator can do that trial or those trials for me, right? But if you're able to categorize a situation that you're working with, like you look at the problem and you say, well, this is just like that other problem I did, and I use this formula, you know, then it's a case of the formulaic approach where there's some defined formula that could be applicable to the situation that you're working with, right? Those are specifically for situations where you recognize that what the problem that you're working on meets the criteria of the formula, right? So the formula has expectations, it has criteria that needs to be met. So you look at it and say, okay, do I meet the let's say four criteria, 4 bits of criteria that are related to that formula? And if I satisfy it, then I can use that formula. But that, you know, I'm just hand waving now, because without seeing some formulas, that one's not going to make too much sense. So we'll sit tight on that one. Estimation, pattern recognition. I make a little note here that this is the least frequently used one mathematically. And what I mean by mathematically is in the math classroom, you know, because it takes time, right? It's research based. So I couldn't give you a question like that on a test involving pattern recognition and estimation, because that usually involves data mining. It also involves, you know, patiently sourcing your information over a lengthy period of time. So you're not looking at a case where it's like, okay, here's a word problem, let me get an answer using estimation pattern recognition. No, that's more like a research project, you know, so that's a different concept, right? But that, you know, practically speaking, that's your weather prediction, you know. So this time of year, historically, the weather, it leads to temperatures that are really high or really low or really somewhere in the middle, you know. In those cases, you can look at, okay, well, what's the temperature normally like in February? You know, in the 30s. Okay, so if the temperature's in the 50s, you're like, oh, it's unseasonably cold, warm, right? So that's how you make those claims, because it's based off of what you've experienced in the past and what is typical for that time of year, right? And it's not just limited to that, you know. So if you know a person, you know, a really good swimmer, a person that spends a lot of time in the water, can hold his or her breath for let's say 3 minutes, right? And then, you know, one day they go into the water, and for some reason they can only hold their breath for like a minute or a minute and a half. The history tells us that individual should be able to hold their breath for much longer, but they're only holding it for a minute and a half. You start wondering what's going on. Are they okay? Maybe they need some tests. Maybe there's something wrong with their lungs. You know, so you're using past information to make predictions about future events, right? Kind of along the lines of correlation and regression. So the example again, you know, weather is the most typical one. That's the easiest one to kind of latch onto. Your basic probability rules, probabilities are always going to exist between 0 and 1. Right? 0 being that the event is impossible, 1 being that the event is certain, it must happen, right? Guaranteed to happen. Not it did happen, it must happen, all right? So the difference there is, I'm not talking about flipping a coin 5 times and getting heads each one of those times and saying, okay, the probability of getting heads is 1. No, because I could have got tails, I just didn't, right? It rained for a week straight. So 7 out of 7, I got rain as my answer. That doesn't mean that it must rain every day. It just meant that it did rain every day for the last 7 days. 1 means that it must happen. So if I'm saying that the probability that it's going to rain is equal to 1, I'm saying that it must rain. No other possibility exists, which we know wouldn't necessarily be true. All right. So what do we do with that information? Well, we have bounds, because between 0 and 1 is where all the other probabilities are going to live. Right? So you got your 0.5, you got your 0.7, you got your 0.128, you know, things like that. Those are all the probabilities that could happen. You can convert those over into percents in order to get a better understanding of what you're dealing with, because a lot of people, they don't really enjoy thinking about probabilities, well, in general, but as like something like 0.3. If I say, what are the chances it's going to rain tomorrow? And you come back with 0.3, I'll know what you're talking about because I do this for a living, but anybody else would be like, why'd you say it like that? You know, they're expecting a percent answer. So our decimal values are between 0 and 1 inclusive, but when we speak in terms of probabilities, very often we speak in terms of percentages because that's just how people talk about probabilities. All right. So the complement rule talks about the idea that opposite values will have, this is weird, just got hung up here somehow. Opposite events will have probabilities that add up to equal 1. All right. So if I say that I have the probability of event A occurring and the probability of the exact opposite of that happening, then those two probabilities have to equal 1. So I'll give you a quick example here. If I were to, I mean, there's an example there, but I'll give you another quick one. Let's say it's the probability of passing a test plus the probability of not passing a test. All right, so I use the little tilde there to represent not. All right, just so happens that when I make the little tilde, it happens to look like an N. So that kind of works, N for not, but it's supposed to be the little tilde. All right, those two probabilities ought to add up to 1. All right, now if you think about it, are there any other possible outcomes when you take a test besides passing or not passing? And if your answer is, well, it depends on the test, then then you agree with my way of thinking, right? Because maybe you were exempted from the test for some reason, like a final exam, right? Maybe the test was organized in such a way that you had the ability to drop it if you got a failing score, you know, like it kind of works in this class where if you meet the attendance requirement, you get to drop your lowest test grade. So that usually means, I mean, I don't know, I can't imagine anybody's going to drop a passing grade when they have a failing grade on their ledger. So if you fail a test, you're going to drop it. So that gives you an alternative, you know? So this really only plays into the cases where you can categorize your events in one of 2 ways, right? But in a lot of cases, you can do that anyway. You just got to get a little creative. So let's say I'm rolling a die and I say the probability of getting a 4. Well, the probability of not getting a 4 would be everything but the 4. But 1, 2, 3, 5, and 6, right? So there's ways of defining it so that it's binomial. Binomial. Well, I guess we could say binomial. I was going to say binary though. All right, one or the other. All right. So now if I attach numbers to these, then it becomes a little bit more obvious. So you got to understand probabilities are dealing with the chances that you're going to meet one of these requirements. It's not a simple proportion of what did happen. It's the proportion of what could happen, right? So it would not be correct if I were to go through, after I finish grading your tests, if I were to go through them and just count up the number of people who passed and the number of people who failed, and let's say the number of people who passed was, I'll be realistic about it, like let's say 25 out of 30 passing papers. And then the other 5 were failing papers for whatever reason. Maybe they didn't show up, maybe they actually failed, maybe they cheated, like whatever, but earned a failing grade somehow. That's just a record of information. Those are counts. Those aren't probabilities, because I'm not able to project out into the future with that information. I cannot now say that an individual's chances of passing the Unit 1 test will be 25 out of 30. It depends on the class, depends on the semester, depends on the mode of instruction. There's a lot of things it depends on, right? It could guide my thinking. I look at it and say, all right, well, let's say it was the other way around, only 5 people passed. If it happened like that, I'd be like, oh, okay, what could I do differently next time? No, like it's really, it's not probability as much as it's an idea for reflection. In those cases, we're talking more about proportions than we are talking about probabilities, right? But the example that we have here, given a multiple choice question with 5 choices, what is the probability of getting a correct answer by guessing? All right, now we're talking probability because it's chance, right? It's a chance event happening. I'm guessing. I didn't study for this test. I didn't study for this multiple choice question. It's got 5 choices. Every answer is equally likely as every other answer because I'm just guessing, right? So I would say probability of getting a correct answer, so probability of correct. Well, it's 5 choices. You got to figure one of them's right. They didn't say anything about it being one of those weird questions where it's select all that applies. It's a multiple choice question, not a multiple guess question. So we're looking at a 1 in 5 chance of getting it right if you were to just guess. All right, so not a good probability. Now the probability of getting it incorrect, so not correct, would be all the other possible outcomes. I don't know which one of the choices is the right answer, but it doesn't matter. I know that there's one of them that's right and the other 4 are not right. Right? So another way I could have done this would have been to say, all right, well, probability of not correct I could think of that as 1 minus the probability of getting a question correct. All right. What I just wrote in red, that's the complement rule, right? Or at least part of it. Right. So I'm looking at just this, I'll highlight it, just this part of it. All right. That's my complement rule. If I want to find the probability of an opposite, I just take the probability that I know, subtract it from 1, and it'll give me the probability of the opposite of that event occurring. Right. So what I could do here is just simply say 1 minus 4/5, I'm sorry, 1 minus 1/5, with a common denominator is 5/5 minus 1/5, which gives me 4/5. Okay, so all of this is the complement rule. All right. Now you may look at it and say, well, why would I ever do it that way? It's a multiple choice question. There's 5 choices. There's 1 right, there's 4 wrong. It's easy. I look at it for situations where it's maybe not so easy, not so relatable. You know about multiple choice questions, but what if you're dealing with a question that's less familiar? Like you're dealing with quality control for a factory, and you're not really comfortable with that information, and you don't have the ability to just kind of determine, all right, well, what are all my possible outcomes? How many are the correct ones? How many are the incorrect ones? I don't know that information. But if I take the number that I know subtracted from 1, that'll give me the probability of the opposite of that event occurring. That's a time saver. And also, in some cases, it's the only way you could possibly get it right. Rounding is going to be really important in this unit. Right? We're going to be rounding to 3 significant digits. Right? So you look at the 2 examples there. They're 2 vastly different examples. But right after those examples, I say, to avoid confusion, perhaps it may be best to stay in fraction form unless you absolutely must use decimals. There will be some situations where you have to go to decimal form, so you can't avoid it. But wherever possible, fractions are going to be your best friend in this unit, right? So when it comes to rounding, what we do is we start the rounding process after the zeros end, right? So you have a string of zeros after the decimal point. Once that string of zeros end, then start counting off 3 digits from there, right? So I have a couple of examples here, but let me just throw in another one for good measure. So let's say you have 0.000, I'll throw in 4 zeros. 1, 0, 1, 9, 2. All right, just made it up off the top of my head. What I would do is I would just start counting from left to right, starting at the decimal point. Now, again, probabilities are going to be between 0 and 1. So I'm not worried about anything to the left of the decimal point, only to the right of the decimal point, right? So I have a 0, so I ignore it. 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 I get to the 1, that's the first non-zero entry. So that's when I start my count. I want 1, 2, 3 values from there. All right, so here's my cutoff. Now I want to round appropriately based off of that cutoff. Right, so I'm looking at this and I'm saying, okay, I got a 9 here. You know the old, if it's 5 or above, give it a shove. If it's below, let it go. Whatever that old saying was. I don't remember learning that as a student, but I've heard it like a bazillion times as a teacher. So this 9 is telling me to take that 1 and round it up. So this in rounded form would be point, and I'd have 4 zeros, 102. All right, so that's my rounded form. And what I typically do, you see I put an equal sign here. I'm going to take that out and I'm going to put a squiggly equal sign. That's the approximate symbol. I'm not going to lose any sleep if you use a regular equal sign, but technically it's not really correct because 0.000010192 is not equal to 0.0000102. It rounds to that value. So it's approximately the same. We can use the 0.0000102 instead of the more lengthy number, but they're not exactly the same. It's close enough, all right? So I'm not going to take off credit if you don't use the squiggly equal sign, but if you want to write it using the correct notation, that would be the notation that you use. All right. So that's a little bit of the introductory stuff. Now we're going to talk sample spaces a little bit, just to kind of refresh our memories on some of this stuff. So we're kicking over to the next page. We got all this stuff over here. Good looking page, good looking resource page right here. And this, you're going to be coming back to this pretty frequently. All right. So, I mean, you You probably didn't need a diagram to show you that there were two sides to every coin. But there it is anyway, just in case. All right. Two coins though. That's where you start kind of getting a little, it starts getting a little crazy. Two coins and beyond. So if I have two coins, what that's telling me, I'll do it in the form of a tree diagram. If I have two coins, the first coin could be heads or tails. So let's say coin one. Now, if I have a second coin, coin two, it's dependent on what the first coin was. Oh, I'm glitching here. I don't know what's going on. My screen froze up. Oh, it just freed up. Okay. Well, hopefully that won't happen too frequently. So if I get a heads for my first coin or a head for my first coin, my second coin can still be either heads or tails. All right, so those arrows, now we usually just kind of leave the arrowheads off, but I'm doing it for a particular reason, because when we use an arrow, it represents a conditional, one, then the other happening. So if my first coin is heads, then my second coin is heads. If my first coin is heads, then my second coin is tails. The same is true if the first coin is equal to tails, because after that I flip a second coin, first coin is tails, flip a second coin, my outcomes are still either heads or tails. All right? It gets a little juicier when you involve a third coin. So let me bring this over here and throw in a coin three. And I'll shrink it all down in a minute, just to make it all look nice like. Right? For each one of those coins, my first and second coin, there is an outcome of heads or tails for the third coin. All right, so I'm gonna use up a lot of space here, then I'll just kind of move it all back together in a sec. All right, so if I got a heads or tails for the first coin, let's say it's a heads. Then for the second coin, I could get heads or tails. Let's say it's a heads. Then my third coin, I can still get heads or tails. All right, in which case I could get heads, then a heads, then a heads, or heads, then a tail. If my first coin is heads and my second coin is tails, then I could be looking at heads, then tails, then heads, or heads, then tails, then tails. Right? So it gets a little bit spicier, but if you have an organizational approach that you're comfortable with, for me, it's drawing, resizing, moving some things around, you know, and then just kind of putting it all in a way that makes sense. That's me, though. Right? You got to do what works for you. So I'll just move this down a little bit. If my first coin and my second coins are heads, tails and heads respectively, then the third coin could still be heads or tails. If my first and second coin respectively are tails and tails, then my third coin could either be heads or tails. It's always the two possible outcomes, regardless of how many trials you're taking. All right. So let me shrink this down a little bit. Line it up, put it all together. Shrink it down and just chuck it over there. So that's a little organizational strategy called the tree diagram that helps you really kind of get a sense of what's going on, rather than being like, all right, well, if I flip a coin once, I can get a heads. All right, if I flip it again, I can get heads and then another heads. All right, so heads, heads, heads. And then you could jot that down. you know, I have it all here, but you'd be like heads, heads, heads. Then you'd be like, okay, then what's next? All right, well, maybe it's heads. Maybe the second coin is a tails, then a heads. Right, so then you jot that down. Then you try heads, tails, tails. Okay. And before too long, you start getting your wires crossed and be like, wait, what about heads, tails, heads? Oh, I already got that. Then what, you know? So what you do is you read off of your tree diagram and say, all right, one possibility is heads, heads, heads. Then you could have heads, heads, tails. Then you could have heads, tails, heads. Then heads, tails, tails, and so on. Right? Before you know it, you've accounted for all possible ways that you could have a distribution of heads and tails among 3 coins. Now, you also see that it starts getting out of hand pretty quickly. You flip a coin once, you got heads and tails. You flip a coin twice, you got the 4 outcomes. Flip a coin 3 times, you got 8 outcomes. 4 times, you could have 16 outcomes, then 32, then 64, then 128, then 256, then 512, then 1024, 2048, and so on. You know, so you're just doubling every single time you add a coin to the mix, right? So it can get a little out of hand very quickly. You just want to make sure that you have an organizational strategy, right? That's why this resource page is going to be really important for you. Now, when you roll a die, 6 outcomes on 1 roll of a die, 36 outcomes on 2 rolls of a die, or rolling 1 pair of dice, right? So you can only imagine when we're multiplying by 6, 3 rolls of a die, that's going to be 216 outcomes. Then I think 1,296. I mean, it's going to get crazy, right? So we're going to need a better way than listing them all out in order to determine how many values are in the sample space, right? But for smaller numbers of trials, it's not too crazy to just list it all out and see what's going on. Like if I were to say, find the probability of getting an even number when you roll 1 die, then what I would do is I would just look at my dice, part of the sample space, focus on the 1 die, and I'd say, oh, I got even numbers here. 3 out of the 6 cases. That's my probability, 3 out of 6. Right? So it's just a matter of kind of taking what you have and evaluating it based off the question. Now, one thing that I've always been kind of under the wrong impression about, and it was like my bad, and it's been for years. So I'm forgive me if I'm going to be very boring about this part of it. Forgive me if I'm boring in general. Cards. When I first started teaching, I assumed everybody knew everything about cards. What I came to understand is that most people did not know much about cards. So I'm gonna talk about a deck of cards as if you've never seen these things before. All right, so that could be frustrating for some people, but I know some people need it. So playing cards. There's a total of 52 cards in a deck. All right. There are 2 additional cards that are included with the deck that are called jokers. We don't use those when we're dealing with probability related to decks of cards. All right. Actually, I think there's 4. There's 4 jokers, right? Honestly, I don't remember. I don't even take into account jokers. So you have 4 what we call suits. All right, those little symbols that are on each of the cards. You have the first row there. It has a little 3-leaf clover, the black one. Those are called clubs. Below that, I think it's obvious. And we have diamonds and we have hearts. And then we have the upside down looking heart, the little stem there, that's called a spade. All right. So those are the different suits. Every suit has 13 cards. All right. Starting with the A, which stands for ace, and going up to J, Q, and K, which are your face cards. You're also known as picture cards, and that's been a source of confusion in the past because there are people that be like, well, they all have pictures on them, so they're all picture cards. No, no, the ones that have faces on them, those are what we call also picture cards, right? That's called, you'd look at it and say, well, the K and the Q are king and queen, so you would think, all right, well, why is that a J? That should be like P for prince or princess or whatever, but it's J for Jack, right? If anything, it should be like the jester or something like that. I don't know, but those are the royal cards, right? So the numerical cards, anything from 2 to 10, those have whatever number is printed on them, right? A, J, Q, and K do not have, in general, there's some games where they do have numerical values, but in general, we treat them as not having numerical values, all right? But the letter A is equivalent to the other letter A. So the A of clubs, the A of diamonds, the A of hearts, and the A of spades, those are all equal in value. It's just their value is the letter A, right? So it's symbolic. It's like algebraic, right? Same thing with the J's, the Q's, and the K's, right? All the J's are equal to one another, all the Q's are equal to one another, and all the K's are equal to one another, right? We don't assign numerical values to those. So for those of you who are big fans of blackjack, forget everything you think you know. No, that's not true. Don't forget, because then maybe you'll lose at the casino, and then you'll blame me. What you're going to do is you're just going to put aside those rules for the sake of your learning when it comes to probability. All right. So that information, in conjunction with everything that follows, is going to lead us to some probability questions that we're going to tackle. All right, so prime numbers, perfect numbers. All right, I put a little notation: use y equals in your calculator as an aid if necessary. So in Desmos or in a graphing calculator, any kind of calculator, you could put it in an equation, and it'll spit out square values for you, or cubes, or whatever. I can show you how to do it on Desmos in a couple of minutes. It's pretty nifty. All right, so the prime numbers, just again, because people forget this sort of thing, it's one of those topics that you don't use it frequently enough that you'd have necessarily instant recall. But when you do use it, it's so like straightforward in terms of the definition that it's kind of hard to forget. But a prime number is any number greater than 1, has to be greater than 1, that is divisible only by 1 and itself. There's other definitions of the word prime, but that's the best one. That's the most user-friendly one. So maybe it's not the best one. It's just the one that people understand the easiest. Right? So I'll just leave it at that. Right? Because you may have learned it a different way. That's the way I like to go after it. And actually, I'm going to move this over. I don't like the way it looks. Dang it. I'm like struggling here, so forget it. I'm just gonna leave it where it is, because for whatever reason my pen wasn't really working. For square numbers, man, it really is glitching, this thing. For square numbers, cubes, and fourths, like I said, you can go to technology for that. We know what perfect squares are. If you take a number and multiply it by itself, you're going to get a perfect square. A perfect cube is when you multiply a number by itself for a total of 3 times. All right, so 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Fourths, multiply a number by itself 4 times. So 1 times 1 times 1 times 1 is 1. If I wanted to jump ahead to like 5 times 5 times 5 times 5, that's going to give me the 625. All right. Let me just show you really quickly what that would look like on Desmos. just because when people aren't really sure whether or not they're dealing with a square, a perfect cube, or something like that, you need something to be able to fall back on, all right? So in order to test to see if a number is a perfect square, we take its square root, all right? So I'll just jot that off on the side to test. All right, so you have a number and you're not sure if it's a square, if it's a perfect square, take the square root. So you take the square root, or you take the cube root, or you take the fourth root. All right, another way of doing that, so or, you raise that number to the 1/2 power, the 1/3 power, or the 1/4 power. So I'll just throw in an example here real quick. Let's say, I got the number 100 right in front of me, so let me do that, 100. So I could pop in a square root of 100 here. If it gives me a clean number, meaning a whole number, then I know it's a perfect square. All right, so we know 100 is a perfect square because its square root is 10. Now, if I pop it in parentheses, type in the 100 and raise it, I use the A to the B power key. And then type in 1/2, same thing. All right, the benefit of doing it this way is that if you wanted to take the square root, you know, you get the square root key, but what if you wanted to take the cube root? I don't see a cube root key there. You know, you hunt around for it in the functions menu, I'm sure you'll find it. But if I wanted to take it simply, quickly, all I'd have to do, let's say for 1,000, is type in the 1,000. Now you see 1,000 not a perfect square, gave me a funky decimal. But if I put it to the 1/3 power, you see it's a clean 10. All right, so I now know that that's a perfect cube. And then I could do the same thing with the 10,000. All right, so I'd raise that to the fourth. You know, 1,000 to the 1/4 power, or 1,000 to the fourth root of 1,000 is not, it's not perfect. So 1,000 is not a perfect fourth, but 10,000 actually is. All right, so you can do it with the fractional exponent using this technique. It's a little bit more user friendly. And again, if you have some really funky number and a funky root, let's say it's a 7th root, 1/7 power. 1/7 power is what I meant to say. Right? So that's pretty nifty. Another technique that you could use is a table approach. So let me just show you that real quick. Plus table. You got a list of values, right? So let me just pop in. I'll pop in 1, 2, 3, 4, and 5. And you see Desmos learned, so it knows that I'm doing consecutive values. So now I could just hit enter. You know, I got up to 5. Now, in my second column, what I could do, instead of having y1, I can do x1 squared. All right, so I just take my x1 column and square all the numbers, and now it gives me a list of perfect square values. All right, benefit of this approach is that I get a full-blown list. So when I'm looking for something like x1, let's say to the 4th power, all I'd have to do is just go down my list and look at it. And I say, oh, 625, it's a perfect 4th, right? Maybe you want it to be a little bit longer. You want your list to be even longer, so go out to 25. Look at all these values I have now. And if you're really savvy about it, what you do is you crank out this, right? So like x1 squared, right? Perfect squares. How about x1 cubed, x1 cubed, geez Louise, and then x1 raised to the 4th power. Now I have 3 lists, all of perfect cubes. And the x1 column is the cube, or the square root of, so they're not all perfect cubes, they're all perfect roots. The x1 column is going to be the root of each of those values in the x2, the x1 squared, x1 cubed, x1 to the 4th. And so you do that, and then you tap on this little little hamburger at the top and just do a quick save. And you call it perfect numbers. So now you have a nice little little resource for you. All right, so you take it away from having to be something that you figure out as you go. You now have a graph that's saved with all that information. That's pretty nice. And also, I mean, it's kind of fun. You don't have to look at the picture, but it's pretty cool. Little exponential, parabolic, you know, polynomial kind of thing going on there. So that's up to you if you want to do the Desmos bit, but I encourage you to make use of the resources that I offer you. So if you don't like Desmos, then start looking for something that you do like, that you can actually make use of, because otherwise you're spinning your wheels. You're not really getting what you need to get out of this. All right. So now what we're going to do is start applying some of this information. Well, maybe not. I forgot I put this page in here. So in a page, we'll actually start applying this information. Well, we do need to talk about Venn diagrams first. So Venn diagrams are really important when it comes to visualizing probabilities and the relationships between sets. I have taken this kind of information for granted in the past, and I've kind of paid the price for it. So I figured I would stop, take some time, talk about a little bit of logic, Venn diagrams before getting into the probabilistic or probability concept. Sorry, I'm really thirsty. So our logical connectives, we got the conjunction. Well, the ones we're going to focus on: conjunction, disjunction, and the implication. If you're familiar with computer programming, then you definitely already know this stuff. But if you're not, then this is going to be pretty important stuff. I have found that the people who have very logic-oriented minds, like your brains are wired logically, tend to do very, very well with mathematics. And the people who kind of neglected that part of their education tend to struggle more than maybe they need to, you know, because if you can kind of get a handle on logic and the progressions of a reasonable argument, then things start making a lot more sense, and you start understanding why things work the way they do. All right, so the notation can be a little bit of a drag, though, because you look at it and you say, all right, well, this is just more stuff to remember. This is not designed to be the kind of thing where it's like, all right, I'm going to test you on logic now. It's more like an enhancement to the content. All right, so conjunction is denoted by that upward triangular symbol. I kind of look at it as like an A without the little crossbar, right? Because that symbol actually means and, right? So that conjunction, this symbol is referring to and. So when I say P upward triangle Q, I'm saying P and Q. And what does that mean? It's if P represents that I am going to tie my shoes, and Q represents I am going to go running. I'm going to go running. And P and Q would be, I am going to tie my shoes and I am going to go running. All right, so it's taking two separate events. If you're thinking in terms of probability, which you should, you're taking two separate events and you're seeing what would happen if those two events would happen in conjunction with one another. All right, so they're happening together. All right, so a little blurb there, if both parts or only both values of P and Q are true, does the expression evaluate to be true? Otherwise, it's false. All right, so if I tell you, and I'll keep it really simple, I am wearing t-shirt, I'm wearing a t-shirt and shorts. If I'm lying about either one of those components, those statements, then my whole sentence is false. So if it turns out that I'm wearing blue jeans right now, then I just lied to you, right? So logic is really just basically if you boil it down to truth or a lie, then then things tend to simplify themselves a great deal. Right? So the overall truth of a sentence, is my sentence true or am I telling you a lie? Right? I am wearing a t-shirt and I am wearing shorts. Right? I'm not going to make a show out of it, but I am wearing shorts. All right? So I'm telling you the truth. Right? So if I was wearing the blue jeans, then I would be telling a lie. All right? Now the disjunction, the V symbol, is an or. Right? That's telling me that I am, or if I want to make it somewhat real world, I am wearing a t-shirt or I am wearing shorts, right? As long as at least one of the parts of the sentence is true, then the expression is true. So if I tell you that I'm wearing a t-shirt or shorts, you see the t-shirt, right? You see that I'm wearing a t-shirt. It doesn't matter whether I'm wearing shorts or blue jeans or something else. I've already got one part of the sentence accounted for, so I'm telling you the truth, right? The other part doesn't matter, right? Very often though, and I'll make a little note here. Beware the either or. All right. So you got to be careful about that, because oftentimes what people will do, let me just kind of clean this up a little bit. What people will do is they'll look at the disjunction as a choice between two possibilities. All right. So if I say I'm wearing a t-shirt or I'm wearing shorts, a lot of people will interpret that as I'm wearing either a t-shirt or I am wearing shorts. So now if I'm wearing both, I'm lying to you, because the either part made it a choice between the two. All right. So just the word or allows for the freedom for at least one part of it to be true, giving you the whole sentence being true. But you throw in the word either there, the interpretation, just based on the way people think, the way people act on a normal daily basis. The word either, whether it's implied or it's overtly stated, tends to lead people to think that it's a choice, right? In this class, the presence of the word or will never be a choice. It'll always be the logic definition of the word or.
So, Professor, I have a quick question. For disjunction,
Sure.
then if we translate that into probability terms, it would be at least one of these events occur?
Yeah, exactly.
Okay.
Very good. Very good. The implication, that's the hardest one. They even say, you know, learning a little bit more about psychology of children with my math for elementary school teachers course, you know, doing a lot of research there. And, you know, one of the last things that develops logically in the minds of humans as you're developing is the ability to reason logically using an implication, right? So the conditional sentences, the if-thens, right? And it's always because it seems cut and dried, but it's not, right? So we have the sideways arrow, that's fine. I talked about that before. The issue is, if I tell you, if it rains, then we will not go outside. You know, like, I'm an elementary school teacher. We're talking about recess, and I tell the students, if it rains, then we will not go outside. It doesn't rain, but we still don't go outside. I got a mutiny on my hands because every one of the kids in that elementary school classroom is saying, but you said if it rains, we're not going to go outside. It's not raining. Right? But in my mind, and the mind of anybody who's logic-minded, and also if you want to be kind of difficult about it, you'd say, well, I never told you what would happen if it didn't rain. I just told you what would happen if it did rain. My promise to you, and an implication is really a promise, and whether or not you fulfilled that promise. So my promise to you is, if it rains, then we will not go outside. The fact that it didn't rain lets me off the hook from having to fulfill that obligation. So it didn't matter. It didn't matter what the outcome was, right? If it didn't rain, if it was a nice, beautiful, sunny day out, and I took the students outside or I kept them inside, I wasn't lying either way, because I never made a promise about what would happen if it didn't rain. My only promise was what would happen if it did rain, right? If you study, then you will pass the test. All right? So you didn't study, but you still passed the test. Was I lying to you? Well, I guess we'll never know because you didn't study. You know? Now, and so I make that sentence, I make that claim, if you study, then you will pass the test. Then you studied like your life depended on it, and you still didn't pass the test. Now I'm a liar. Now I'm wrong. All right? I implied that something would be true, and it was in fact not true. All right? Now, that's a silly implication for me to make to begin with. I should never make that statement. If you study, then you will pass the test. I mean, that's very vague. Study what? You know, study geometry? You know, like, I got to be a little bit more specific on what you need to study. But if I make that claim and it doesn't pan out, then I'm the liar, right? But if you didn't actually study, then you can't come back at me and say, well, you said that if I studied, I'd pass the test. Well, did you study? No. Well, then what are we talking about? You know, like, it's not even a conversation, all right? People have a lot of trouble with conditionals, and so you got to imagine that if these three concepts not only occur in everyday life logically, but also have a translation to probability, then the corresponding probabilities are going to be a little bit on the tricky side also. So we got to be careful about that. Okay. The Venn diagrams help us to organize our thoughts, because we say the intersection between two sets, or the overlap between those two sets, that's what happens if you have a conjunction.
Wait, Professor, sorry, going back one more time to the implication. So then,
Sure.
in terms of probability, that would be if P occurs, then Q2 must occur, or no?
Yes and no.
I still don't understand.
Yeah, because that's the thing. Like, we really got to dive into that, because the conditions here, if P is true, then Q must also be true.
Yeah.
Right? So that's the one thing that we're going to latch onto. But we also have the possibility that if P is false, Q can still be true.
Okay.
So that's where the probability part of it is going to get complicated, because I'll show you in symbolic notation. These are the ways that you could have a true sentence that involves an implication. You could have true then true. All right. So I made the promise and I kept the promise.
All right.
you can, so true then true is going to give you a result that is true, right?
Right.
But false then true, or false then false, those are also going to be true. Because that's the case where it didn't rain, but I could do whatever I want because I never said what would happen if it didn't rain.
Yeah.
So it's still a true sentence. The only case where it'll be false is if I didn't keep my promise, where true then false. You know, I said if it doesn't rain, then we'll go outside. You know, I changed it up a little bit. If it doesn't rain, we'll go outside. It didn't rain, but I lied. I didn't take the students outside. That's where I didn't come through on my promise. This is the only instance in which a conditional sentence will be false. So when it comes to the probabilities, we need to be prepared to account for all three of these possible cases.
Okay, that's clear.
All right. So visually, it's very easy to identify the and the or situations. The notation's a little on the kooky side, but when I show you how it relates to the conjunction notation, it's a little bit easier to understand. So this is set notation, that upside down U and the U. This is the same as A and B. And this one is the same as A or B. All right. So in the case of a Venn diagram, we think of each circle as representing a set. And what I'll do, just to make it a little bit clearer, is I'll redraw the circles separately on the side. All right, so this one here is my set A. Oh, it's supposed to be red. And this is my set B. All right. When we're talking about, over here. When we're talking about the intersection of two sets, you kind of think of it the way you would like the intersection between two roads. It's where the two roads are in common. You know, that box, that square that's created, you know, don't block the box. That's the intersection. It creates an area, a common area that's part one road and part the other road, right? So what we have here, when we're talking about the intersection between two sets, is where I take one set and overlap it with another. All right. Though the area of overlap, and actually, let me get a little cute here real quick. I'll just save that for a minute. All right, that area of overlap, that is the intersection between the two sets. All right, so that part of it there is we call it the intersection, but most people are comfortable just saying the and. You know, the part that's both A and B at the same time. All right. So, yeah, that's going to be better than me marking up the other diagram. Yeah, so, well, I guess I could still mark it up, but that's this region right here. All right. Now, when it comes to the or case, or is trickier because what I'm saying is if either part of the sentence is true, then the whole thing is true. All right. So if I tell you that, again, I'm wearing a t-shirt or shorts. If I'm wearing a t-shirt, I'm telling the truth. If I'm wearing a t-shirt and jeans, I'm telling the truth. If I'm wearing a polo shirt and shorts, I'm telling the truth. If I'm wearing a t-shirt and shorts at the same time, I'm telling the truth. If I'm wearing a polo shirt and jeans, That's the one case where I'm lying. I'm not telling the truth there. All right. So if A is true, the whole thing's true. Right. So I'll make a note of that. If A, so I'll say true if A is true, B is false. A is false, but B is true, or both parts are true. All right. So if I have two overlapping circles here representing the two sets, I would be looking for any part of A and any part of B, including the overlap between A and B. All right. So it'd be pretty messy for me to shade the entire diagram, the red and purple one. So what I'll do is I'll shade the other one. So any of the two circles, including the overlap. Would allow for truth. All right. So then the only way it's false is if it's neither A nor B. All right. So A is false, B is false. So that's everything else in that rectangle is going to be the case where A is false and B is false. All right. But as long as I have any part of A or any part of B, including the overlap, then I'm good to go. All right. Then we have the not A. The not A is kind of tricky because it depends on how you designate your information here. But if we're going with the same idea that A and B are the two circles, then when I say not A, so what I'll do is I'll just snag this diagram for A. I'm gonna pop that in there. Here's A, all right? That whole rectangle is the entire sample space, the whole shebang. When I say not A, I'm saying everything but A. So if I'm shading here, I'm shading every part of the rectangle that doesn't include the circle A. So all of that stuff there is not A. Every little bit of it. Trying to make it a little bit nicer. All right. So that one's a little bit easier to talk about in terms of real terminology because it's like the rain versus not rain, pass versus not pass, getting a question right versus getting a question not right. You know, like that's a little bit easier to understand. It's just kind of putting all this stuff together. So you look at the examples that follow on a Venn diagram, shade the regions corresponding to all this stuff. You're like, oh man, this just got really real, really fast. And so, and I promise you, this is just the foundational stuff. So you're like, wait a minute, it's just foundational. It's going to get worse. No, what I'm saying is if we can get a handle on this, then the stuff that follows is going to be a lot easier. All right. So when I say A, U, not B, the first thing that I would want you to do is think of it in terms of real verbiage here. So the alternate notation, A or not B, okay? But then I would even take it the next step and say, all right, that is the same as saying or. All right, so A or not B. All right. So what I'm going to do is I'm going to identify circle A, and I'm going to identify what not B looks like. All right. And you know, sometimes you got to make side diagrams here and then just kind of puzzle or piece it together in your mind. So here is A. Right? We're very familiar with A at this point. Right? We've been doing that for like 5 problems already. So that's my A. Right? So I got that. Then I need or not B. Right? So not B is everything outside of B. All right. So in order for an or sentence to be true, either part of it needs to be true. All right. So I want to account for every part of this diagram that is either inside circle A or outside circle B. All right. So let me just pull circle A out for a sec here. I'm just going to move this over. And then what I'll do, and this is the benefit of having an app, you know, it's not always going to be pretty, but if you can do it with a little bit of technology, it kind of goes a long way, right? So here is the whole sample space. All right, so I just shaded the whole rectangle. I want everything outside of B, so I don't want that shading inside of B, right? So I want my shading to be outside of B. And that'll be my not B. All right, so that's the not B part of it. So in order for an or sentence to be true again, either part needs to be true. So I got to be inside of A or outside of B. I got my outside of B, so now let me get my inside of A. So let's bring my inside of A back. Anything inside this red circle is also fair game, right? So I'll just do that in red, and I'll shade in a little darker everything inside that red circle. So the only part of this that's not going to be considered part of the solution would be the part that's just B itself. All right. So what we actually came up with, and this is the power of the Venn diagram and logic, and it's if it seems so stupid that we're doing this, it's because we haven't made this connection yet. If you look at this now, what we just discovered is that A or not B is the same as just B all by itself. All right. Which means if I'm trying to figure out a probability, and it said, find the probability of A or not B. Find the probability that you're wearing a t-shirt or you're not wearing shorts. So then all I'd have to do is figure out the probability that I'm only wearing shorts. So only B, no A. And I would have the same answer. All right. So being able to make that transition from one form to another. Now, I'll say it's convenience at this point, but it's actually more than that. Because we're looking at it as like, it really is going to be a matter of necessity, right? Because there are going to be some probability questions where you're like, I can't do that. You know, I'll give you a quick example. And I'm not going to go through the math right now because that's a different story for a different day. But if I tell you that I need you to find the probability of, if you were to roll a die 10 times, find the probability of getting at least 1 4 when you roll the die 10 times. That rightfully so should sound like a nightmare, right? Because that means at least 1 4. That means that maybe the first one was a 4 and the rest of the values were something else. Maybe they're all 4s or everything in between, right? There could be hundreds, there could be thousands of values. If you got to figure that out, it'd be crazy. But if I tell you that using a Venn diagram and a little bit of logic, that I can take that problem that would take you the rest of your life to figure out and make it into a 2-step, very quick problem, that I think you'd sign up for that pretty quickly. All right. Now, I know this is going to be a struggle. I don't want you to spend too much time going nuts over this, but what I'm going to do is I'm going to put a star on each one of these remaining problems, ask you to look at it between now and Wednesday, because it's not going to do us any good if I just take you through all these problems without you having an opportunity to look at it first. All right. So try these problems on your own. If you don't get it, if you don't make some headway with it, that's fine. I'm going to go over them again. Or I'll go over them anyway on Wednesday, but I want you to have had a look at it before I want you to kind of struggle with it a little bit before I give it all away at the end.
Wait, can I hustle you for some extra credit then if we get it in before Wednesday?
Normally I'd say yes. I got answer keys for this stuff online.
Okay, fine.
That is totally a legit question. And under other circumstances, I would totally say yes, but this is the one case right now.
Professor, number 3, is it not A or B, or it's something like a multiplication? I don't know.
No, it's not A or B. Yeah, you had it right.
Okay, perfect.
And that's not the same as saying if we took the parentheses away and instead put the not sign in front of A and then B. It is not the same as saying not A or not B, correct?
Correct.
It's different.
It's different.
Yeah, got it.
All right. All right, so I'm going to stop the recording.